Hi, I'm Bruce Momjian, Postgres core team member and EDB employee. 2 years ago, I gave a talk at Tid Scan called Explain the Postgres Query Optimizer. And today I'm giving the follow-up to that talk called Beyond Joins and Indexes. The talk is basically taking, building on the basics of Explain the Query Optimizer, talking about all the other things that the optimizer does that I didn't get a chance to talk about 2 years ago. So I'm looking forward to this talk, and I hope you enjoy it too. This is, again, a follow-up to a previous talk I gave 2 years ago called Explain the Query Optimizer. If you're interested in the slides for this talk or any of my other 62 talks, the URL right here is where you would go to find that. And, of course, the QR code works as well. So, basically, 2 years ago when I talked about Explain the Query Optimizer, I covered the basics of the optimizer. That is, how does it work? How are optimizer statistics used? What are the various join methods possible? The various scan methods, including use of indexes. And I concluded talking about the limit clause. This talk is going to talk about everything else, every other thing that the optimizer does. And frankly, it took me a long time to basically distill this list down to those sort of, I want to say the word fancy or sophisticated methods that the Postgres optimizer can use. And you will kind of, at the end of this talk, get a feeling for how much it's capable of doing. One of the great things about SQL and relational databases, frankly, is the ability to take a query that's normally written in an English-style language and convert it to something that is optimized and executes very quickly. And we're going to go through, again, 43 examples of this. As you can see at the bottom right, we do have 68 slides, so I'm not going to be able to go into a huge amount of detail on anything, but I will give you a general idea of what it does and why this thing is so cool, at least to me. We do have some controls that turn on and off various optimizer settings. In the top left, these are all the settings that I covered in my previous talk explaining the Postgres Query Optimizer. And what I am going to talk about in today is this middle section, these incremental sort here all the way over to Tid Scan. The bottom left, bottom right, where we talk about partitioning. I do have a separate partitioning talk where I cover those. And again, there's a link there at the bottom if you're interested in that material. So let's start with the simplest one. The simplest one is a result node. It's basically just returning a constant. Not a whole lot of fancy things we can talk about here. One thing I do want to highlight, though, is there is a link here at the bottom. All of the SQL you're going to see today is in that SQL file. If you download the slides or you go to that URL, you can actually run this presentation and watch all of the output that you're seeing today. Value scan. This is actually a special scan node for the values clause. You may not have seen the values clause, but the values clause is part of the SQL standard and allows you to basically output multiple rows. A function scan, it would be used if you have a function that returns multiple rows. In this case, generate series is an example of that. And you typically put that function inside a from clause so that the function becomes a source of rows which are used in the rest of the query. Incremental sort, this is the first one that I think is sophisticated. And we've had this for many years. It effectively allows you to use an index for the early parts of an order by and to do manually sorting for the latter parts of an order by. Here, we have an index, we have ordering by X comma Y. We have an index on X, and we're going to do an incremental sort. We're going to use the index for the X part. We're going to manually sort the Y part. This is the first diagram that you're going to see that covers basically internally what is going on inside. As you can see on the left, all the blue is pre-sorted. The pink side on the left is not sorted. And incremental sort is basically retaining the blue sorted part and merely sorting the pink part within equal values of the blue part. That's how a multi-column order by works. Anyway, but we're not resorting the X field. We're using the index to resort that. The unique clause used particularly for something like distinct. If you're familiar with the distinct clause in the target list, as I'm highlighting here in blue. And another way you can get distinct is a union. This is a special clause that joins two selects together. This is not the same as union all, but actually union where duplicates are removed. And that's why the unique clause is used here. Here's a diagram of that. To do unique, we basically sort the result, and then we remove adjacent duplicates. That's the easiest way to get uniqueness. The append node, you would primarily see this with union all. Again, union all does not remove duplicates. It merely appends the second result of the first, and we get a very simple append operation out of that. Merge append, this is a pretty sophisticated capability. If you're familiar with a merge join, it's basically a merge join style union of two result sets, but you're appending the values together instead of joining them. Here we have a query up at the top where we order by two, we have a values clause, we order by the first values clause, we do a union all, we order by the second one, and then we effectively have two ordered result sets. We want to append them together. That's what the append node does. We just learned that. So what we're effectively going to do is we're going to take the two nodes, we're sorting them already, and we're going to merge append them, which means we're going to take two result sets. We're going to take the lowest value out of each result. We're going to put that into the result, and then we're going to take the next lowest value between the two sources. That will be our next result, and then basically walk down through the results that way. Subquery scan and hash setup. This is something you would use for something like an except clause. An except clause is where you're basically removing rows from the first result that appear in the second result. And to do that, we effectively need to create a hash. So as you can see from left to right, we take the two results, we join them in a hash, and then effectively we can see which cases where we have a result from the first that does not have an accept or a removal from the second. So any case that has a 1 result without the 2 result is effectively what we output. You can see from the results here on the right, 7 and 12 are the only cases that have a 1 without a 2 in terms of sources. And that's why you get the 7 and 12 coming out of that result. Sort up, this is for intersect. This is where you have two results. You want all the rows that are in both result sets. And in this case, we do something very similar to unique. We basically take the two result sets, we sort them, and then we figure out which ones have a 1 and a 2 for the result. And again, in cases where we have a 1 and a 2 together, we output those. A 3 and a 6 are the only ones that are in result set 1 and result set 2 at the same time. Materialize, this is effectively a node that takes particularly a sequential scan in this case and brings it into memory. It's a case where we bring some results into memory. Usually it's not a big result set. And we're going to do it in memory because it's easier than if we're going to revisit something over and over again, in this case, a not equal join. It's faster to do it in memory than to be reaching out to the shared buffer cache over and over again. And that's what's happening here. And we're just basically materializing the right-hand side into local memory, and then we do the join on the left here. Memoize, this is kind of a new one. Introduced, I believe, in Postgres 14. This is a weird one that I wasn't super excited about. It has all these weird requirements of when we actually use the node. But surprisingly, there's a lot of cases where Memoize speeds up queries. So the requirements in using a Memoize is you need a lot of duplicates in one of the result sets, and it needs to be too small for a hash join. So that's your one requirement. The second requirement is you have a result set that's too big for a hash join. and it's also unique. And then you also have an index. So again, you can see why I was not super excited. It feels like, is this really going to be used at all? But when you think of the thousands and millions of queries that are run, there are a large number of cases where this is happening, many more than I realized. So here's an example of one where we're doing basically a small table joined to a medium-sized table, and we already have an index, and you can see the Memoize happening here. What Memoize, and we have a nice URL there at the bottom if you want more details, but what Memoize effectively does is it allows you to create, remember what I talked about Materialize, and it takes the results out of shared buffers, and it moves it into memory, and it's more efficient doing it that way than having to go to shared buffers all the time for the rows if you're repeatedly looking at the same rows. Well, in this case, we've already defined that the right-hand side is too big to be pulled into memory completely. So what we do is we just cache the frequent lookups that we have. So we kind of create a Materialize, but not a full Materialize. We create a cache of materialized values. So we basically start on the outer side. We do a lookup. If the lookup shows that the entry is not in the cache, then we go to the shared buffers. And if we find a match, we copy that into the cache. So later lookups can use that copy. If we find that we don't have an entry, we have a separate recording that something was not found, that we've remembered that. So we don't continually look up missing entries either. So what happens here is effectively we're now doing a join. And again, this is a case where we have a lot of duplicates on the outer side. So we're going to continually be looking for the same values in that cache over and over again. But because it's smaller, we don't have to bring the whole thing into memory. It's actually really efficient. And again, this was a big win for Postgres 14. The group clause, you might not have realized you can use the group clause outside of an aggregate, but you actually can. It just basically removes duplicates. If you're curious about how that works, again, feel free to read that text at the bottom. A group clause basically takes multiple rows and distills them down to one value. Aggregate, you've seen this before. Here's a simple count. Here's a group aggregate where we have count and group by together. Okay. And we're basically taking multiple rows, moving them into a single row if they have identical matching columns defined in the group. But we also have a special aggregate field that allows us to take those multiple values and sort of aggregate them together, whether it be sum, average, standard deviation, maximum, minimum, and so forth. That kind of allows us to kind of shrink those down. And that's what group by does effectively. Hash aggregate, this is a case where, and again, it's different than a hash join, okay? This hash aggregate is where you're aggregating not necessarily by bringing things down, but by creating a hash and then accumulating the values in the hash. And this is kind of the way it works. You have the outer side, or you have your full table on the left, and you're basically going to distill that down to specific values on the right. But again, we're doing this in a hash, so it's very easy for us to find matches and to aggregate those. Mixed aggregate, if you're familiar with roll-up, this allows you to kind of do several levels of aggregation at the same time. This is, again, sort of the way it works. You're getting an aggregation, but then you sort the result and you can get other results. Sort of you're aggregating, and then you can do further operations on those aggregates. Maybe you want to find a total. You want to report the total and then the individual aggregate total separately. It's kind of cool. Window aggregates, I do have a long window function talk. Again, URL there at the bottom. But effectively what window aggregates do is to allow me to do aggregation across multiple rows, but I do not lose the distinctiveness of the individual rows. So as you can see, I have, 10 rows or something on the left. I have 10 rows on the right, but I'm able to aggregate across these groups at the same time. And that's really the special value that window functions give you. Getting into parallelism. This is, again, a whole complex field of what Postgres can do for parallelism. I have several slides related to parallel operations that Postgres can perform. The ones I'm going to talk about first are parallel sequential scan, parallel aggregate, gather, and finalize aggregate. Here, a very simple sum on a large table effectively creates two parallel sequential scans at the bottom, which then become partial aggregates, which are then gathered together in the primary backend process and then finalized. And hopefully you can read this, but again, going from left to right, we have parallel sequential scans happening in two ways in the same table. So we only have one table here on the left, but you can see I have two worker processes. One is parallel scanning from the top, and one is parallel scanning from the middle down. Going from left to right, I then aggregate these results together into a sum, for in this example, between the two workers, and then I send them to two workers send them to the primary process, where we then go to gather. We gather results together, and we issue a finalize, and the finalize again is returned to the user. So you can see why a large sum on a large table can be sped up by using parallelism. Gather merge, a little different. It's sort of, we're getting a little closer to merge join or merge aggregate, right? Remember, or merge append, right? See, that merge concept is sort of reappearing. Here we're taking a large table, we're doing order by. So how do we do that? Similar process. We have a large table on the left. We have two parallel sequential scans working. These two parallel sequential scans are individually, each worker is sorting its own results. So we have two sorts going on in parallel, okay, the top one and the bottom one. And then when we want to return the result to the user, instead of using a partial aggregate, which we can't because we're not using aggregates here, we're going to do a merge gather, similar to the way we did a merge append. We're going to take the lowest value from either of the result sets. That'll be our first result. We'll then go advance, take the lowest value from the two result sets. That'll be our next result. And we just keep going down until we get to the last row and the last result. And eventually we end up with a sorted result. And we've been able to sort them independently. Again, you can see that merge capability reappearing here in a parallel situation. Parallel append. This is very similar to the merge append, where we're just appending results. Here we have a huge table, union all with a huge table. We just want to append the one huge table to the other. And again, this diagram is a little bit crazy, but we actually have four parallel sequential scans going on because we have two tables. Then these are being parallel aggregated into two result sets and then sorted independently and then appended, parallel appended into the results. So again, because if you notice, we do have an order by here, so we have to sort it at the end. But the point is that we've been able to append the two. We've been able to do two sequential scans in the same table and then merge those together. Parallel hash join. This is the case where you're doing a join in parallel. I know this diagram is kind of off the charts, but I'm going to walk through that. You have to kind of go like back and forward here. What we're going to do is we're going to take this table in two pieces. We're going to take this in two pieces. We're going to create a shared hash of this large table. We have two parallel sequential scans on the same table. We're going to create a shared hash between the two workers, and then the outer side is going to do lookups against that shared hash and then report their results back to a gather node. I know it sounds like crazy, but it actually works really well. Again, this does allow us to take the inner side, do two parallel scans, and create a parallel hash, a shared hash that we can then look up from the outer side. Moving on and going to some of the more sort of SQL specific nodes that we have. Common table expression scans. I do have a very popular common table expression talk, again, here at the bottom right in blue. Common table expressions are basically the ability to run a query and then use its result in a later part of the same query. You can see that here. And effectively, all we do is we basically create a common table expression, what we call a CT source, and then we can basically use that in a later query. You may be more familiar with recursive common table expressions. This is very good for walking through trees and sort of dynamic content. Again, you can see in blue here, we have the with recursive. We also have with recursive union. This is the way it works from the SQL level. You have a primer that loads into source, and that source then feeds into a second query, typically after a union all, which then feeds up into source again, and you get this loop going on. Internally, this is the way it looks. You have your sort of primer that goes into the recursive union. It then loads up a work table. The work table then is fed up into the recursive union. And as you're generating rows through here, you're effectively appending results to the CTE source. And as soon as your work table is empty, your common table expression at the top is done. And then you use your CT source in the rest of the query. So effectively, you're looping around but the upper part of the common table expression until it returns no more rows. Then once it does, that section is finished. We have a CT source, and that passes down to the lower part of the query. To get a little more, even more exotic, ProjectSet would be used if you have a row producing function in the target list, not necessarily in the from clause, which you talked about earlier. Here we're putting this row result function in the target list. Again, Postgres can handle that. If you're doing for update, you get lock rows. If you're doing a sample scan, a table sample, we have a special node for that. If you're doing XML table, we actually have a special node just for XML table because the syntax you can see is really unusual. If you're using foreign scans, we have the capability of doing that. If you're doing debugging or you want to look at physical rows in storage, those are called TIDs, tuple identifiers. You can actually use this syntax right here. There's an invisible field called CTID, which allows you to specify, for example, page 0, the first tuple on page 0, and I can actually access that directly without having to use an index or a sequential scan. I can go right to that location. And this is effectively the way it works. If you're doing an insert, we create an insert node. If you're doing an update, we do an update node. If you're doing a delete, we do a delete node. We do not create nodes for truncate. Truncate is not what we call a DML. It's a DDL. It does not go through the optimizer. And therefore, you cannot run explain on it. It doesn't create a special node. It's sort of its own thing because truncate effectively removes all the rows immediately from a file. If you're using the merge command, we do have a merge node that allows you to effectively run the merge operation. Semi-join, this is kind of interesting. I didn't really understand all the details here till I sort of dug into it, but a semi-join is effectively similar to an in clause, except you stop on the first match. So it's sort of like exist is saying, do I have any rows? If I do, return the outer row. If I don't return it. So it's similar to a join between two sources, except you're stopping after the first match. That's why it's called a semi-join, because you're not joining all the rows, you're just joining the first match and stopping. Another example of semi-join would be an in clause. Again, is the value in that subquery, yes or no? In and exist are actually equivalent because they handle nulls the same. An anti-join, this is kind of interesting. This is when you're starting to use something like not exists. Again, same logic. Is there a row in there or not? I stop the scan after my first match or my first negative result. A not in, and this I learned as part of doing this talk, is a case where remember I said exists and in are kind of the same in terms of their handling of nulls. Not exist and not in are different in their handling of nulls. If you've ever gotten tripped up by this, be careful. If you're not in returns a null result, you will not get any rows. So just be aware of that. Again, feel free to read the text at the bottom. This is kind of a cool case if we know you're not going to return any rows because we have a unique index and we do a left join, the join goes away. I was kind of surprised by this in doing my research for this talk, and that's kind of cool. It knows it doesn't need to do the join, so it doesn't do it. I didn't cover tuple store and custom scan again. Not really important. So again, I'm loving the fact that I was able to take a talk I did 2 years ago that gave the basics and was able to really flesh it out in a comprehensive way to give you a good explanation of all the power that is available in the optimizer. And again, Postgres is continuing to get better. I just worked on the Postgres 17 release notes. There's a lot of optimizer improvements coming, even in this release, again, due probably September, October of 2024. Thank you for attending this talk.